It's Dr. Ken here with you, and this is my mid-semester AC review. So this is for students who are halfway through the AC unit. So from my experience over doing this for many years and marking many hundreds of assessments, here's what I found at the mid-semester break. Many students can't tell their AC from their DC. You can only use DC relationships in AC when current and voltage are in phase. That is, the circuit is purely resistive. Example, power equals the volts times the current, or if you have the total current and the total voltage, then you could also use an Ohm's Law approach. Apart from then, you cannot use Ohm's Law. In all AC circuits that have reactive components, that is, they've got capacitors and or inductors, the voltage and currents are not in phase. Therefore, we can't use simple Ohm's law. We've got to take into account the angles. For example, in single phase, power equals the volts multiplied by the current multiplied by the cos of the phase angle, or what we would call the power factor. So you need to be able to understand the difference between those two things. I find many students trying to apply Ohm's law in AC circuits without them understanding that Ohm's law will only work in a purely resistive AC circuit. The next thing I've found is that many students can't tell the difference between the voltage applied versus the voltage drop in a circuit. So the voltages applied come from our base load generators, particularly in New South Wales where I'm based, in the Hunter Valley. You can't slow them down, you can't change their frequency. The supply voltage won't change ever. So that's the applied voltage. The voltage drops are the voltages caused by the currents through your circuits and your components. That is, through your resistors, your inductors and capacitors, whether they're connected in series, parallel or combinations of the above. They will vary in magnitude and in direction, but in relation to the supply, which is the reference. So in a series circuit, the reference is current, because it's the one common thing through a series AC circuit. In a parallel circuit, the reference is voltage, because the voltage is the common thing in a parallel circuit. So you must understand the difference between voltage applied and voltage drops around a circuit. It's all about the current. Only current does real useful work when it passes through a resistance. There is always heat and there is always magnetism as a minimum. May also produce movement, mechanical force, light, chemical reactions, etc. But the thing I want to get across to you, in an AC circuit, the only part of the circuit that does any work is the current through the resistances in the circuit. Again, many students seem to think that the current through the capacitors and the inductors do active work. No, there's current there, but it does not do any productive work. The next thing I found is students were struggling with their engineering units. So it's time to go over those again. Going to start here in the middle of the table with the number 1, or what we would call unity. So any number times 10 to the 0 is 1, and anything times 1 is itself. So we call that unity. Going up the scale, thousands times 10 to the 3. The name is kilo, as in kilogram or kilometre, thousands of, and we use a lowercase k. In our case, quite often, kiloamps, thousands of amps, or kiloohms, thousands of ohms. The next one is times 10 to the 6, or mega. So, as the name implies and sounds, it is millionths. So if we have mega ohms, we have millions of ohms, and we use the capital M. Now here's the one that I found a lot of students have tripped over, the milli. Going back the other way now, milli is thousandths times 10 to the minus 3. They often think, oh, milli, that must be millions. No, unfortunately, milli is thousandths. So a milliohm is 1,000th of an ohm times 10 to the minus 3, and we use a lowercase m as the symbol. The millionth is the micro. So times 10 to the minus 6 is micro. The next thing students seem to struggle with is being able to remember the different aspects around an AC waveform. There are 9 basic aspects or attributes that make up an AC waveform. There is the instantaneous values, which I'm showing here with the red arrows at any point on the curve. We have instantaneous values. Then we have in black the maximum values. We have a maximum positive and a maximum negative. That's from 0 volts to the top of the wave max or to the bottom of the wave minimum in the opposite direction. Next we have the voltage peak to peak or the current peak to peak. It doesn't matter. Our peak to peak value goes from the top of the max pos to the bottom of the max neg. A lot of students were given peak to peak values and couldn't work out how to calculate the max value. It's simply half the peak to peak. Or if you have the max and you want to find the peak, you simply double the max. Next is the average at 0.63. It's nice to know, but for a sine wave, it's not particularly useful. The next is the RMS value, the root mean squared at 0.707. This is the effective DC value of an AC waveform and will play a significant part in how we do algebra and mathematics and geometry with AC waveforms. Then measuring the horizontal, we quite often will do that in time. Our standard 50 Hertz AC waveform in Australia is 20 milliseconds for a whole period, or 50 Hertz, in other words 50 times a second. We also measure the horizontal of the waveform with angle 0 through to 360. You can see there on our drawing 0 degrees, we cross over at 0 volts or amps, we get maximum at 90, back across 0 at 180, we get minus at 270, and then back to 0 at 360. So we have these single phase attributes, and there's 9 of them, but that is far too many to deal with. By the way, for many of my students, we had put a picture of this on the back of the equation sheet. All you had to do was turn it over and have a look. So how are we going to deal with these 9 attributes? How are we going to condense them down into something that we can handle? Well, the first thing to remember is these attributes can be applied to all different kinds of AC quantities. And the first of those is voltage, current, and resistance. We can apply those values to all those kinds of things. Also, we can apply it to inductive reactances and capacitive reactances. And finally, we can apply it to impedances. So what are we going to do if we want to take those 9 attributes, here they are, the whole 9 of them, and we want to condense them down, or as I say, smush them into something that is useful? This is how we do it. We want to make a phasor, which is a graphical representation of these values of voltage, current, resistance, inductive reactance, capacitive reactance, and impedance. Now we've always got to start with a reference, and the reference always goes left to right and is horizontal. So the first thing we do is we need a magnitude. Now, and a magnitude equates to the phasor length in millimeters, and represents its RMS value of current, voltage, resistance, capacitive reactance, inductive reactance, or impedance, but it is the RMS value, and its length represents the magnitude. The next is the direction. The direction equates to the angle plus or minus, or we may use the word lead or lag, so many degrees from the reference. Angle does not work in isolation. It must work in reference to the angle. So is it leading or lagging the reference? Or is it plus degrees above the reference? Or is it minus degrees below the reference? So direction is our second quantity. Our third quantity is rotation. All phases are rotating anti-clockwise. So they're all spinning around anti-clockwise in relation to each other and to the reference. So let's quickly review series AC circuits. I had a lot of students tell me that I could just algebraically add up all the voltages around an AC circuit and it would give me the volts total. Unfortunately, this is not true because that does not consider all the angle relationships between resistors, inductors, and capacitors in a series circuit. So let's remind ourselves how this works. In a series AC circuit, current is the reference. So, because it is the only constant in the series circuit. The next thing is we add the voltage across the resistor. Now it's in parallel with the current. Its phase angle is 0. It has a phase angle, but its phase angle is 0 degrees. Its length represents its voltage in millimeters. Then we add the voltage caused by the conductor. Now, we're dealing here with practical inductors, so I've drawn in a couple of degrees to allow for the internal resistance of the inductor. The inductor is close to 90 degrees in the vertical position for current. In other words, the current is lagging behind our inductive voltage. Then we add the capacitive voltage. Remember that current always leads a capacitor. So there are the basics of our phasor diagram. But of course, no phasor diagram is complete until we've added them up. So let's add them up. This one nice and easy first. So we're simply adding VC to VR, do a parallelogram, close the hypotenuse of the parallelogram, and there is volts R plus volts C. Next, we've got to add the volts, that purple phasor, to our orange phasor because we didn't include the orange phasor on the first edition. So our second step now is to do a parallelogram between the purple and the orange phasor and then draw in volts total. So there we have it. The phase angle is between the black phasor and the horizontal, and the length of the black phasor is our voltage total. And here's our finished phasor diagram. We can also do a nice little shortcut. So we can actually just do a simple voltage triangle. So I'll show you how we do that. We simply put the voltage for the resistor on the horizontal, then we subtract the voltage from the inductor from the capacitor from the inductor, I should say. We're going to assume they're 180 degrees apart. They're not most of the time. There's a few degrees between them. So like I said, this is an approximation. Then we simply do our parallelogram again, close in the horizontal, and there's the volts total. But there's an even shorter cut to that. We can simply close the hypotenuse of the triangle. It's the same thing as the parallelogram. Just remembering our phase angle now is on the right-hand corner, not the left-hand corner. but the hypotenuse is the voltage total. So it's a quick way, done to scale, that will help you check your phasor diagram. And there's our finished voltage triangle. So what about series resonance? Students again seem to struggle with series resonance. This is the phasor diagram for series resonance. Nothing more, that's it. This is because the XL and the XC are the same and they have effectively cancelled each other out, and it's called series resonance. Only the resistance is effective in the circuit, so the circuit is said to be resistive. Very high voltages will occur across the capacitor and the inductor only. Yes, the voltage across the resistor will go up a little, but nowhere near as dramatically as across the capacitor and the inductor. And of course, this is dangerous to human life and can cause the capacitor and or the inductors in the circuit to fail. So now we move on to 8 parallel AC circuits. Similarly, I had students tell me I could just add up all the impedances. They remembered that they had to get the branch impedances. Then they thought, I'll just add up all the branch impedances and they could use that to work out the current total. Unfortunately, again, that's not true. Again, doing that does not allow for all the angles that the currents are at. Yes, we have to calculate the impedances to work out the currents, then put the currents in at the appropriate angles onto a phasor diagram, and then we can work out the I total. So let's quickly go through that. This time voltage is our reference, of course it being the only constant in a parallel circuit. We put our current on the phasor diagram in parallel with the reference because it has a phase angle of 0. Then we add our current through the inductor, and of course the inductor current lags the voltage, which is what it's doing here, and then we add our capacitor current, which leads the voltage in the upwards direction. Again, we've got our 3 phases onto our phasor diagram, and now we need to add them together. Again, go the simple 2 first. The 2 are 90 degrees to each other. A nice simple parallelogram. There is IR plus IC. Now do a parallelogram between the purple phasor and the orange phasor. Again, go from where the parallelograms intersect back to the origin, and there's our I total. Also giving us a phase angle, in this particular case, below the horizontal, so it's a minus phase angle for I total in reference to the voltage. And here's our finished phasor diagram. We can do a quick current triangle, nice quick shortcut. Again, we can put the current on the horizontal. We can take the current through the inductor, subtract it from the current through the resistor, put it on the vertical, do a parallelogram, get the I total, and again we can use a nice little shortcut and just go across the hypotenuse of our right angle triangle, and there's the phase angle and the I total. Again, it doesn't account for a little bit of angle in a practical inductor, but it's quick, short and dirty and gets you to an approximation of the answer. Parallel resonance. Here's the the phasor diagram for parallel resonance. Only the current through the resistor is operating in the circuit. Again, XL equals XC, but this time it's called parallel resonance. Only resistance is effective in the circuit, so the circuit again is said to be resistive. You get high recirculating currents between the capacitor and the inductor only. You get some small voltage increase across the capacitor and the inductor caused by the internal resistance of the inductor and the high currents flowing backwards and forwards. There's danger to human life from high temperatures, and also the high temperatures may cause component failure. Only the resistance at the end of the day takes any current from the supply. 11. The impedance triangle. Good old Z. So again, a lot of my students seem to struggle with the impedance triangle, or when to use it, probably more than the triangle itself. So the resistance on the horizontal, represented here by the black. Again, R is always in phase, so it's on the horizontal. And on the vertical, we have the XL minus the XC. We simply do a parallelogram. A lot of students forget that an impedance triangle is just a phasor diagram between the reactances and the resistance, and there's the impedance. But of course, we can close the hypotenuse of the triangle again to get Z, and we end up with our nice impedance triangle. So with the impedance triangle, there's a couple of ways you can get a big Z, the total overall circuit Z. Always encourage my students to think Ohm's law first. If you have the voltage total and the current total, then you can work out the total Z of the circuit. If not, you may have to go the second approach, and that's to use Pythagoras. So that's to use our Pythagorean equation here of Z equals R squared plus XL minus XC, and then square it. I had a lot of students who squared the XL and the XC and then did the subtraction. No. You must subtract the XL and the XC first. Then if you need to find XL or XC, then you will need these equations. And if you're halfway through AC, then these equations should be stated to become automatic. XL is equal to 2 pi FL, and XC is equal to 1 on 2 pi FC. 12 is our power triangle, and this is just a natural progression from the impedance triangle to the power triangle, because all we've done is we've simply multiplied all the impedances and reactances by the current to get the power. But again, students seem to struggle here. So real power, as I stated at the very beginning, this is the only place any work is done. That is the power that is emanated from the resistive component in the circuit. The reactive component is always on the vertical, either up or down, depending on which of these is bigger, and it's always going to be the XL minus the XC. So the reactive inductance minus the reactive capacitance. And then finally, then of course multiplied by current to give us reactive power in VAR. And then finally, the apparent power, which is the power that looks like it's being taken from the power supply, but it's not, and that is simply the volts times the amps, or what we quite often call VA, just volt amps. So constructing our power triangle, we simply need real power in watts on the horizontal, reactive power in volts amp reactive on the vertical. Again, it is just a phasor diagram. Do the parallelogram, and there's the answer, the blue phasor. But of course, we can just close the hypotenuse, a bit quicker, a bit easier, and it gives us the apparent power S. So apparent power S, volt amps, reactive power Q in volts amps reactive, and real power in watts. So here are our equations around the power triangle. We'll start with true power. So power is the volts across the resistor and the volts in the resistor itself. So volts and current through the resistor. But if you don't have that, and that's common that you don't, then you have to default to this one. The total voltage, total current multiplied by the cos or the power factor. You can also use P equals I squared R, again, if you've got the current through the resistor and the resistance. You can also use power equals V squared R, again, voltage across the resistor and the resistance. And we can transpose Pythagoras to say power is also equal to S squared minus Q squared. Next, we have the reactive side, the Q. Again, you can use an Ohm's Law approach, but only if you have the voltage across the reactance and the current through the reactance. And again, that tends to be rare. More often than not, you've got the voltage total and the current total. And you then multiply this time by the sine of the angle. And with true power, you can use I squared X. You can use V squared X as long as you have all the appropriate values. And then finally, again, transposing Pythagoras, we can use Q equals V square root of S squared minus P squared. And finally, apparent power. This is the most common equation. S equals the volts times the current. Volts total times current total is going to give you S. And because this side of the triangle is also the Z of the impedance triangle, if you know Z, you can use I squared total multiplied by the Z, or you can use V squared total divided by the Z. Or our normal standard equation is we use S is equal to the square root of P squared plus Q squared, our standard Pythagorean arrangement. And finally, the power factor is the cos of the angle, and that ratio can also be found with the true power divided by the apparent power, or P divided by S. And you can see here I've highlighted the equations. These are the most common ones that we tend to use. So for S, it's these two. For P, this one you should always commit to memory. This one would be used a lot. This one you can get by transposing the Pythagoras. And then Q, again, this one is worth remembering. To get Q, this is probably the most typical and the easiest way to get Q. And finally, you can also transpose to get Q using Pythagoras. How to solve AC problems that is absolutely foolproof, but my students, no one seems to care. But I'll explain it to you anyway. Step 1, draw and or redraw the circuit diagram. Quite often in assessments, you're given a circuit diagram that is partial and you're told to add a capacitor in parallel, or you're asked to add a inductor in series. So draw and or redraw the circuit diagram. Do the same for a phasor diagram. Even if you don't do the phasor diagram to scale to start with, draw the phasor diagram relationship. It'll get the picture in your head about which is leading, which is lagging, where everything is in relationship to each other, depending on whether it's a series or a parallel circuit. Then you need to ask yourself a series of questions. The first is the solution a scaled phasor diagram of voltage or current? Is it that straightforward? Then ask yourself, is the solution an impedance triangle? Am I being asked to calculate Z's and XL's and XC's? Those kinds of things. So is this an impedance triangle? Then finally, is this a power triangle? Am I chasing apparent power, reactive power? All those kinds of things. And then one final question. After asking yourself those three questions, you should have determined what part of the physics you're playing with. Then ask yourself, do I need 2 steps to get to the answer? Quite often in the assessments, they give you enough information for 2 parts of the problem, so you have to then work out the third. So it's a 2-step process. So ask yourself, do I need 2 steps to get to the answer? Then select the appropriate formulas, transpose them as required, and you need to be very skilled at transposing because equation sheets that most students have only give you the equation in one form. So make sure you know how to transpose them quickly and easily. Then estimate the answer. I'll be very blunt. If you can't estimate the answer, then you do not yet know and understand the physics. You should be able to look at a series circuit, look at the impedances around a series circuit, and estimate the kind of overall impedance and the voltages. So when you punch it into a calculator, you're expecting an answer around 12 volts, and you get an answer of 13.2. You go, that's close, that is probably correct. But if you get an answer of 132, then you can say to yourself, I've made a mistake. Calculators only give you what you punch into them. So be very careful. Estimate your answers and then do the maths. That's the final step. Then do the maths. If the answers come out close, you know you are spot on. Many of my students, I use this little analogy about being present, precision, and practice. So I'll remind you all once again. Presence. Make the most of your time and access at your tech, at your registered training organisation. Make sure you do the practicals. Don't let your mate do the practicals. Make sure you each have a go at the practicals. At many techs, you work in teams of 2 or maybe sometimes 3. Make sure that someone else doesn't do all the work and you just fill in the numbers. You will not learn the pracs. You must be present in the application of the physics, so make sure you do the pracs. Take advantage of tutorial nights. I don't know of any RTOs, and I know a lot of them, a lot of techs, and they all offer tutorial evenings. Make sure you take advantage of those. Precision. A lot of people think that precision is about the maths. No, 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 no. It's not about the maths. It's about precision of the physics. So make sure you understand that resistance, current, is in phase with the voltage. Inductance, current is behind the voltage or lags behind. Capacitance, current is in front of the voltage. Friends, that is the physics in 3 very simple sentences. That is the physics. Yes, there's about 9 ways those 3 things interact, which add and make the complexity. But that is the basics. That is the physics. Those 3 things are the basic physics of AC. You have to wrap your head around those, or you will not be able to be precise in what you do in AC. Practice. Put in at least 2 hours a week practice. I have taught AC in many, many RTOs and locations, and you need to put in, the average student, 2 hours extra every week in practice. If you're fortunate enough to have access to energy space, then use the energy space exercises to do the practice. Your RTO probably has an eLearn site where there's lots of resources, videos and things. There's the textbooks. I like the one by Phillips personally. It has a great approach to AC physics. And there's plenty of other places that you can get practice, practice, practice. One more thing. Learn to embrace the suck and develop mental toughness. Now, I'm not being glib here at all. If you get a chance, look up this guy, John Fawkes. He talks about hardcore evidence-based fitness and self-improvement. And this is what John says. In the military, this concept is called embracing the suck. which is defined as to consciously accept, and I've put in red, appreciate, because if you can even appreciate that it's difficult, something that is extremely unpleasant but unavoidable. The term has seeped into common language lately, which is great because it's an awesome attitude to have and really helpful for any kind of self-improvement. But John has never seen anyone offer up a simple method for actually adopting that attitude. Mostly the advice has been boiled down to you just have to do it. But there actually is a method, and it's shockingly simple. It's a simple body language hack. And this is the lady who has it. Her name is Amy Cuddy. So again, if you have a few minutes, it's only 18 minutes long, have a look at Amy Cuddy's TED Talk. She talks about body language. Now, for a long time now, we've known that we can tell what people are thinking and how they're feeling by their external body language, etc. But what Amy is saying is it's a two-way street. If you actively change your own body language, your posture, the way you carry yourself, it actually changes the way you think and learn. So body language, this is a new revelation to me. I had no understanding that body language works in both directions. So body language, the way you posture yourself, if you do that actively, it actually will help your learning. So finally, this is Dr. Ken's 1/3 rule, and I find this, like I said, I've been teaching AC for 25 plus years, and this is what I find. 1/3 of my class embraces the difficulty of AC and have disciplined themselves to achieve what is required, and they're achieving it. The next third think they're achieving what is required with a minimum effort. They have deluded themselves and are not achieving what is actually required. It just superficially appears that way. Then I have 1/3 that know they're not achieving what is required, but they don't know what to do about it, are just simply hanging on by the skin of their teeth, hoping that something is going to change. So what can we do about that? Here's what we can do. The first group, keep doing what you're doing. Whatever it is that you're doing that helps you learn and embrace the challenge of AC, keep doing it. The second group, ask yourself, are you in this group honestly? And if you are, make some changes. If you can honestly ask and answer that question, you're halfway there. Having decided that yes, I'm just getting past on the minimums, then yes, you're going to have to double your learning effort and engagement. I'm sorry, that's just the reality to make it through. Group 3, decide to make some learning changes. Talk to your employer, talk to your teacher, talk to the student counsellors, but talk to someone and make a plan about how you can go about changing how you're going about your learning in AC. Now you'll notice I've used some colours, traffic light colours, green, orange and red. It's the red group in the middle that concern me every single semester. The people who think they're doing just enough to make it and often get to the end, and in competency-based assessment, they get one or two things wrong at the end, and I'm sorry, that's it. You're back to do the whole unit again. So please, if you're one of those in the middle, ask yourself, honestly, am I doing just enough? If you are, start doing more. So that brings us to the end of Dr. Ken's AC review. I hope you've enjoyed learning a little bit more about the challenges of AC.